pathogen identification, reliable results with clear interpretation. This webinar focuses on the role of internal controls in real-time PCR-based pathogen identification, and will cover the challenges in molecular pathogen identification, different types of internal control suitable for real-time PCR pathogen identification, and then introduce QIAGEN's novel universal internal control for use within laboratory developed pathogen detection assays. It's now my pleasure to introduce you to Dr. Lillian Roth. Dr. Roth is the head of animal pathogen assay development at QIAGEN. She holds a degree in veterinary medicine from the University of Leipzig and a PhD in natural science from the Technical University of Berlin. Before joining QIAGEN in 2009, she conducted research at the Free University of Berlin, the Federal Institute for Risk Management, and the Technical University of Berlin. Once again, please feel free to send us your questions during her presentation, and we'll address them at the end. Now, without further ado, I give you Dr. Roth.
Hello, everyone. I also welcome you to today's webinar. Thank you, Keith, for the kind introduction. So, Keith, is the screen okay?
Yes, it is.
Okay, thank you. Today I will talk about internal controls for real-time PCR-based pathogen identification. Okay, I will start with giving you an introduction to the use of controls in real-time PCR. And additionally, I will talk about some general aspects of internal controls, and after that, I will introduce QIAGEN's new internal control concept to you and show you some application examples. At the end of the session, as Keith mentioned before, I will answer your questions that might come up during the presentation. So let's start with a short introduction. During the past years, pathogen identification by real-time PCR has become a standard method and is rapidly replacing classical culture-based methods. Sequence amplification and real-time detection with sequence-specific probes is fast, sensitive, and specific. However, real-time PCR requires the use of appropriate controls to enable the correct interpretation of analysis results. Only by using the right controls you can spot false positive and false negative detection signals. And this is the prerequisite for reliable real-time PCR results. Let me show you some examples of real-time PCR interpretation. It is commonly known that such a sensitive method as real-time PCR requires the use of controls that rule out false positive results which might be caused by contamination. This is done by use of negative controls, such as no template controls or negative purification controls. And these controls will verify that the positive result is a valid positive result and is not caused by contamination. While the use of negative controls is generally well established in most labs, the fact that false negative results can also be a risk in real-time PCR is often recognized to a much lesser extent. PCR is an advanced and highly sensitive technology, but still false negative results are possible and they do happen. False negative results can be caused by several factors, like for example errors in sample extraction or thermal cycler malfunction. But probably the most common cause for false negative results is the failure of reverse transcription or of PCR amplification due to inhibition. Typical inhibitors which might inhibit PCR and which can be carried over into the PCR are heme, biosalts, urea, but also high amounts of background nucleic acids can cause inhibition. One basic approach to identify PCR inhibition that is sometimes used is to spike one aliquot of the sample with a target sequence and then do a separate extraction of this aliquot and detect the target in PCR also in a separate reaction. This is feasible, but it involves a high workload, and it also results in many extra samples, which of course costs cycler space and also costs money. The more practical and efficient way to control for inhibition and for other malfunctions is the inclusion of an internal control, meaning the simultaneous extraction and or amplification of the pathogen target and an internal positive control within the same tube in a duplex reaction, and that's doing this for every sample. And by using internal control, PCR and inhibition and other malfunctions are ruled out. The internal control should always be combined with at least one external positive control reaction per run. This should be done in addition to using the internal control just to prove the functionality of the reaction mix for amplification of the pathogen target. And now together these two controls will confirm that your negative result is truly negative. Next, I would like to describe some general aspects of internal controls. There are several technical approaches of internal controls. Endogenous internal controls, or ICs, occur naturally in test specimens, such as, for example, a sequence of the host genome as beta-actin, or such as a sequence from normal microflora genomes, for example, 16S sequences. Regarding exogenous internal controls, exogenous internal controls are spiked into samples, either during nucleic acid extraction or before PCR amplification. And they can either be homologous, meaning that the internal control has an artificial template which is constructed to carry the same primer binding sites as the targeted pathogen sequence. Differentiation between the pathogen target and IC amplicon is then done by using a different probe. Heterologous ICs, on the other hand, are designed with their own primers and probes, which are entirely different from the pathogen assay. Each of the different internal control approaches has advantages and disadvantages. The advantages of the endogenous internal controls are that the template is present in the sample already, so there is no need to add anything to the sample. Also, endogenous ICs can be used as a control of cell lysis as well. This is an interesting feature for some applications where it is important to validate if the sample has been taken correctly. For example, when you are looking for an intracellular pathogen in swab samples, it can be good to see that you had host cells in there, so it indicates that the sample has been taken correctly. A disadvantage of this approach is that the starting amount of the IC template can be highly variable depending on sample type and on sampling technique. In case of viral RNA applications, a higher starting amount can also be due to enhanced expression levels of the internal control due to disease-related cellular pathology. Now, a very high starting amount of an endogenous IC template can impair the assay sensitivity for detection of the target. This can be due to competition of the internal control assay and the pathogen assay for reaction components in the PCR. Other disadvantages of the endogenous internal control approach are that different host species and sample types may require different endogenous IC designs. And endogenous ICs do not allow for differentiation of extraction and amplification failure. In the context of exogenous homologous ICs, an advantage that is often mentioned is that the same primers are used for the internal control assay and the pathogen assay. By this, amplification efficiency is supposed to be identical for both. However, I see this definitely more on the contra side, because using the same primers will unavoidably lead to competition between pathogen assay and internal control assay, and this again may lead to a reduced sensitivity for detection of the pathogen target. Additionally, IC template design and synthesis are quite complex and cannot be done by every lab. Due to the fixed primer binding sites, the options for a sophisticated internal control assay design and setup are also very limited. Moreover, for each new pathogen target, a new IC template and IC assay needs to be designed. So both endogenous and exogenous homologous ICs carry the risk of impairing detection sensitivity for the pathogen target due to competition for reaction components, either because of varying amounts of starting template or due to primer competition in case of the homologous IC. Additionally, both endogenous and homologous ICs involve tedious internal control design, and their use is restricted to few applications or even to individual assays. On the other hand, exogenous heterologous ICs allow the use with a defined and consistent amount of internal control template. They offer unrestricted options for functional design and optimization of IC properties to ensure that there is no competition between pathogen assay and IC assay. And only an exogenous IC system offers the possibility to be used with various assays. As a downside, heterologous internal controls can not be used for validation of the sampling procedure for some special applications, for example, for swabs when looking for intracellular pathogens. So all in all, each of the internal control approaches has its own value for specific applications, especially when it is used in the hands of PCR experts. However, in the context of process safety and also of simplification of workflows, only exogenous heterologous ICs allow for an IC design and setup that prevents competition of the internal control and the pathogen target. Moreover, heterologous ICs are suited for universal use for several assays, and they make the implementation of new assays easy. So why is the IC design so important? Well, here are two examples of what can happen if you work with a poorly designed internal control. If the internal control assay is functioning too strong or too weak, this may impact the interpretation of results. First, if the IC system is stronger than the pathogen system, the internal control signal might be unchanged in case of inhibition, while the weaker target system is negatively influenced. As you can see here at the top, where the CT stays at CT29 for the internal control. No matter if no inhibitor is present in the reaction, or if a low amount of inhibitor is present, or also in case of a strong inhibition. At the same time, the target clearly reacts to the inhibition. It's negatively influenced. With a low amount of inhibitors present, the CT is shifted a bit, and with strong inhibition, the target drops out completely. So if this happens, then in the worst case, it would mean that you would have the risk of a false negative result here. In the other case, well, the IC system should always be a little bit weaker than the target system to prevent the case that I just described, because this may never ever happen. However, if the IC system is much weaker than the target system, if it's really too weak, then this can also cause trouble. Even the slightest degree of inhibition might lead to IC failure, as you can see here, even although the target might not have been influenced at all. The consequence is that many true negative samples would give questionable results, meaning that all these samples need to be retested. So as you can see, the IC design is very important because poor design can corrupt the functional quality of the internal control. As a summary, an ideal IC for clear and reliable result interpretation should be non-competitive, so that it has no influence on the pathogen target amplification, and the IC system should neither be too strong nor too weak, but should correctly indicate inhibition, being in correspondence with inhibition of the pathogen target. And furthermore, an ideal IC system should allow for universal use with various assays to eliminate the need to set up a new IC system for each new assay that is to be implemented. So all these points we had in mind when we developed the new QIAGEN internal control system, which I would now like to introduce to you. The new QIAGEN internal control concept is based on a highly sensitive real-time PCR chemistry for either PCR or one-step RT-PCR pathogen identification. The pathogen target is co-amplified with QIAGEN internal control for verification of negative results. And the internal control concept is generic for universal use with various pathogen assays. The IC is exogenous and heterologous, and it carries a unique artificial sequence that is not present in any biological sample material. There is no competition of the pathogen assay and the internal control in duplex PCR due to the strictly non-competitive IC design and the pre-optimization with the corresponding PCR chemistry. The internal control indicates inhibition correctly and reliably, and it can be used with most existing or new real-time PCR assays employing dual-labeled probes without the need for optimization. Two variants of IC systems are available, a DNA IC for co-detection with viral or bacterial DNA or also with fungal DNA, and an RNA internal control for co-detection with viral RNA. The internal control DNA or RNA can either be added before PCR or RT-PCR for use as an amplification control, as you see in the above picture, or it can be added before the extraction for control of both nucleic acid purification and amplification. The internal control is provided as a component of the new Quantifast Pathogen+IC kits. The Quantifast Pathogen+IC kits are available as PCR or one-step RT-PCR kits. Included is a 5x master mix, which allows for a high sample input volume. Up to 12 microliters of sample can be added to each 25 microliter reaction. The internal control assay includes a mix of primers and probe for detection of the internal control. It is provided in a lyophilized format. In internal control, a DNA or RNA template for use as an amplification control, meaning to be spiked into the PCR, is also provided. It's also provided in a lyophilized format. Two separate ROX vials of different ROX concentrations allow for use of the kits with different real-time PCR cycles. The RT-PCR kits, which content you can see below, additionally contains the Quantifast pathogen RT mix for the reverse transcription step. All the user needs to add now is the primer probe mix for the targeted pathogen, which might be a self-designed assay or an assay from literature, and of course sample nucleic acids. Additional internal control DNA or RNA templates are provided separately for optional use in the extraction procedure. These templates are higher concentrated to allow adaptation of the internal control starting amount, to different elution volumes after the nucleic acid extraction. As I mentioned before, the Quantifast Pathogen+IC kits can be used with most existing or new assays. However, for ideal duplex performance of the pathogen and the IC assay, some design guidelines should be considered for the employed pathogen assay. The probe of the internal control assay is labeled with MAX, which is a fluorescence dye which is equivalent to Hex or Joe or Vic. For the pathogen assay, we recommend using FAM as a reporter dye, and we recommend using a non-fluorescence quencher, such as, for example, black hole quencher. For optimal performance, the pathogen assay should be designed to work with a typical two-step cycling protocol with combined annealing extension at 60 degrees Celsius. Specialized software, like for example Primer 3, should be used with standard algorithm parameters to design the primers and probes, and the primers and probes should be designed with standard real-time PCR melting temperatures. And the amplicon size should be below 150 base pair for optimal performance. These recommendations all correspond to the standard design recommendations which apply for the design of efficient real-time PCR assays. So therefore most assays in literature and self-designed assays have been designed according to these guidelines anyway. Therefore the internal control is compatible with most established or published assays. Now I will show you some application examples. During the development of our internal control system, it was very important to ensure that the internal control does not impair the sensitivity for the detection of the pathogen target in any way. Therefore, during optimization, we constantly compared singleplex amplification of the pathogen with co-amplification with the internal control. The resulting final internal control system contained in the Quantifast Pathogen+IC kits has no influence on amplification of the pathogen target. In the example shown here, the serial dilution of bovine herpes virus DNA from viral culture was detected without or with the internal control on the rotor gene Q. The setup was done according to the handbook without any optimization. Here the gray amplification curves show the signals for singleplex BHV detection. When you look now at the blue curve, these show the the signals for the BHV duplex amplification with the internal control. Above here in red, you see the signals for the internal control. As you can see, the curves are absolutely congruent, the singleplex and the duplex curves. This shows that the internal control has no influence on the CTs or also on the shapes of the amplification curves in comparison to singleplex detection. The corresponding standard curves show that the precision, the efficiency, and the linearity are very high, and they are also identical for BHV co-detection with the internal control in comparison to the singleplex detection. You can see again here the blue duplex curves overlaying the gray curves for the singleplex detection. The error bars represent plus minus 1 standard deviation here, and they're smaller than the data points in most of the cases. That's why you can't see them. We tested the Quantifast Pathogen+IC kits for many different pathogen assays, which we chose randomly from assays which were published in literature and from own or also from customers designed assays. Duplexing of any given pathogen assay with the internal control worked always without optimization for both DNA or RNA targets. A few examples of DNA and RNA targets are shown on this slide. Again, blue duplex curves always in correspondence with gray singleplex curves in every case. Maybe I would like to mention this special case here, this BRSV, bovine respiratory syncytial virus assay, is always a nice example. It's an assay that was randomly chosen from literature and, primer probe system that was chosen from literature. And it has a very low efficiency and is generally not a very nice performing assay. Efficiency is something like, I don't know, the slope is minus 3.65 or something. It has low efficiency, but surprisingly, even the performance of this deficient assay was not impaired by duplexing with the internal control, as you can see here, showing again that the internal control system is designed and set up to be absolutely non-competitive. So we made sure that the internal control assay has no influence on the target assay performance. But what about the next points I mentioned before? An ideal IC system should neither be too strong nor should it be too weak, as this might lead to false negative results in one case or to increased frequency of retesting in the other case. The QIAGEN internal control reliably indicates inhibition by CT shift or by signal dropout. In this example, you can see two concentrations of norovirus RNA, which are detected in duplex with the internal control, resulting in CT values of 27 and 30. The internal control has a CT value of 29. In this reaction, there are no inhibitors present. Now in the middle you see that when a low amount of inhibitors was present in the reaction, 25 nanogram of humic acid in this case, the norovirus signals show a shift of about 2 CTs. This is reflected by the internal control signal, which actually shows a shift of 3 CTs. This is a representative result, as the internal control system is adjusted to be always a little bit weaker than the pathogen system in order to prevent that the internal control might drop out after the target. With a very high amount of inhibitor here on the right side, 100 nanogram humic acid in this case, the norovirus signal drops out completely, which is also reflected by internal control dropout. So what does this mean for the interpretation of your results? I will show you on this slide. When the internal control is used as an amplification control by addition to the master mix, then the internal control signals in the no template controls always serve as a reference for the internal control CT value that you expect in your sample reactions. If you add the IC to the extraction, then the IC signal in the negative purification control can serve as a reference. So let's pretend these 3 amplification plots here are plots from unknown samples. On the left side, you see a negative detection result for triplicates of a pathogen target. At the same time, in the IC channel, the internal control has shows CTs of 29, which correspond to the CT of 29 in the no template controls. This confirms that no inhibition or other malfunction occurred in the reaction, and thereby it validates this negative result as a true negative. In the middle, you can also see a negative result for the target. And these reactions, however, the internal control shows a shift from CT29 to CT32. This indicates that the reaction was slightly inhibited. This also means that the amplification for the target has also been slightly inhibited. For most applications where medium to high pathogen loads are expected in the samples, this would still be a valid negative result. Only for applications where very low concentrations of the pathogen target need to be detected in this T range of like 37, 38, something like that, this CT shift of the IC would warn that detection of the target might have been impaired. On the right side, again a negative detection result for the pathogen. In this case, there is a complete internal control dropout, which indicates that the reaction failed, meaning that the negative result for the pathogen here is not valid, but might be a false negative result. This slide shows an example of how we use the internal control system for our routine development work and how nicely the internal control indicates inhibition. It's just with like a snapshot from our work. It's not about real-time PCR here, but about sample extraction. And you can see various blood samples. And into these samples, an identical amount of RNA virus has been spiked. And the samples were extracted and were detected with Quantifast Pathogen+IC kit on the QIAextractor. The reactions are more or less inhibited depending on the individual samples and also depending if an inhibitor removal step had been done or had not been done. In the top figure here, with the violet bars, the dark bars show the CT values for the viral RNA without inhibitor removal, and the lighter ones show how the CT was improved by inhibitor removal treatment. For example, you can see here an ovine blood sample on the left that was only very slightly inhibitory without inhibitor removal. And the other two here are two porcine blood samples that were more inhibitory. In this case, the IC shows a strong shift from about 27 to 32 without inhibitor removal. And in this case here, there is no signal for the viral RNA at all. And these different degrees of inhibition also for the other samples for the viral RNA detection is perfectly reflected by the results for the internal control, as you can see in the lower figure here with the blue bars. For this exemplary ovine sample, the CT shift for the internal control is also very low and identical to the target CT shift for the viral RNA. And for the two porcine samples, there's also a strong shift for the first one, corresponding to the viral signal, and there's also complete dropout for the second sample, corresponding to the viral RNA result. So, as a conclusion, valid real-time PCR results require the use of adequate controls, and careful internal control design and setup is the prerequisite of a functional internal control system. The new Quantifast Pathogen+IC kits provide highly sensitive and fast real-time PCR or one-step RT-PCR. They increase process safety because the kits allow the correct interpretation of negative results through co-amplification of the user-defined pathogen target and the internal control. The QIAGEN internal control system is based on a non-competitive design and setup. It accurately reflects inhibition of the target system, and the internal control is compatible with most standard real-time PCR assays and eliminates the need for optimization of duplex setup with the target. The internal control can be flexibly used as PCR or an extraction internal control. The Quantifast Pathogen+IC kits run with fast universal two-step protocols which allow for parallel readout of different pathogen assays and easy implementation of new assays. Okay, that was all for today already. Thank you very much for your attention, and I will now be happy to answer your questions. And we'll hand back to Thies.
Right. Thank you very much, Dr. Roth. I appreciate that. Very, very interesting presentation. What I'd like to begin with is a couple of the questions that were presented during Dr. Roth's presentation. And again, if you have anything that you would like to add at this point, please feel free to do so. And we will try to address everything with regard to how long this will go here. Okay, the first question is, what is the nature of the internal control?
The internal control templates are naked nucleic acids